In this video, we're going to practice just designing a mechanism. So here you have a reaction. NO2 plus carbon monoxide becomes NO and CO2. Effectively, an oxygen's transferring from one molecule to the other. Well, the real rate, when experimentally determined, is constant times concentration of NO2 squared. So we have two options I'm going to help guide you with here. Try and come up with a mechanism where in one case you're going to produce N2O4 as an intermediate, and another where you're going to produce NO3 as an intermediate. These will be two separate ideas for a mechanism. See if you can come up with a mechanism for either of these that would reproduce this observed rate law. You can determine whichever step that you invent is the slow step and see if you can devise a mechanism where with either of these intermediates you're able to determine a slow step where the NO2 is second order. Give that a pause, give it a try, and come on back. All right, if you're back, well, let's play these two. I want to make N2O4 as an intermediate. So let's just have one step where N2O4 is an intermediate, and I'm going to have a second step where that's going to get used up. Well, how do I make N2O4? Well, that's 2 nitrogens, 4 oxygens, and I have half that in each of my NO2s. So what if I had 2 NO2s just combined? What if they ran into each other and made N2O4? All right, that would work. I'd use up some NO2, I'd make some N2O4, and then that would have to react with my carbon monoxide. Well, that's 2 nitrogens, 4 oxygens. One of those oxygens is going to move on to the CO to become CO2, which leaves me 2 nitrogens and 3 oxygens to work with. Well, I could have N2O3, maybe that gets formed. And maybe there's a third step. Maybe my N2O3, well, if we think for a minute, I still haven't formed NO. So I need to make some NO. So maybe that just breaks off. Maybe 1 nitrogen and 1 oxygen leaves. That also leaves me 1 nitrogen and 2 oxygen remaining. Well, that gives me an NO2 in my products, except, hey, I had 2 in starting materials over here, and I only needed to use up 1 in my reaction. So if we think about the Hess Law for this, if I add these up, it does add up to my balanced reaction. I put 2 NO2s in, 1 comes out, so I net only 1 NO2 going in. 1 CO went in on the left, 1 NO came out on the right, 1 CO2 came out on the right. My N2O4 was canceled, my N2O3 was canceled. So yeah, these 3 elementary steps would return the observed balanced reaction. Could we possibly get our real rate law from this? Well, if our first step was slow, because that would have 2 NO2s, and, well, there's no earlier steps, and 2 NO2s is what we expect to see. So this could work. This could be a mechanism. What if we tried to do that with NO3? So I want an intermediate of NO3. And I'm going to have at least a second reaction where NO3 is going to go on to do something. Well, how could I get NO3? I'd need nitrogen and we need to acquire some extra oxygens. Well, I have NO2. Well, if I try to take oxygens off of carbon, I'm headed the wrong direction. But what if I stole one from another NO2? One of these oxygens pops over. That'd give me an NO3 and an NO. So I've actually made one of my products. I know I want NO. What if I just take one of the oxygens off and put it onto the other NO too? Result would give me an intermediate of NO3. Well, that needs to ditch its oxygen, so CO still needs an oxygen. It could transfer it over. Goes back to NO2 and now CO2. Well, again, if you think about the Hess Law bit, I put in two NO2s, but one comes out, so the net is only one on the left side, which is what I wanted. One CO went in on the left, got one NO out on the right, got one CO2 out on the right. And my NO3 that was an intermediate got canceled to make the process happen. So here's a mechanism as well. This one only required 2 steps really to play out. And, well, again, if our first step was slow, then it would be dependent on the reactants in that step, and that's 2 of the same starting material. We'd get the same rate law. As long as the first step was slow for both of these, we couldn't actually determine between them. At least not kinetically. There's some spectroscopic methods. Depending on how fast the later steps are, it's possible you could build up an incredibly small amount of N2O4 or of NO3. You might be able to spectroscopically see a little bit of that appear. Effectively, you'd have wavelength and absorption, and what will happen is you'll have an initial spectra, and over time that'll decrease as it becomes the products. And you transition to just having your products. But during the reaction, it's also possible that you might see a little peak show up a little bit. That peak would kind of maintain as the reaction happens. If that peak is the intermediate, then it will decrease towards the end and it will go away. And so sometimes it is possible to spectroscopically watch for those little intermediate peaks. You might be able to spot, say, NO3 or N2O4 or N2O3. That could help you determine if one of these mechanisms was more likely. So the idea of how do we kind of think about elementary steps, what could combine to make certain intermediates, guided here with a few suggested intermediates to look at. And an important note to that, kinetically alone, we could not determine between these two. If the slow step had been other steps, well, then we'd have a more complex rate law, and so we could rule out some of these if our slow step wasn't the first step. But in this case, either of these with the first step being slow could be the real mechanism. We do not know, and from rate data alone would not be able to determine. Here's a little practice on just thinking about how to construct a mechanism. Simple transfers, one atom or one bond usually, 2 molecules coming together or one breaking down. How can we rearrange things to produce the products that we expect? And do any of those rearrangements and selections of which step is slow allow us to reproduce the observed rate law?